All right, so good morning, good afternoon, and good evening, everyone. And welcome to our last day of Women in Astronomy Working Group training program session, the first session on essential skills for astronomy research. And this is the last day of the training program. And today we are going to cover more on Astropy. We will see how, we have seen already how to download data from the archive. And today we are going to use Astropy and plot the data and try to understand what our data shows to us. And this part of the program will be given by Professor S.N. Hassan. So he is going to take over. He's going to start, and then it will be finished by Priya Hassan. So Professor Hassan, could you please take over?
Yeah. Hello.
Thank you.
Welcome everyone to the last day of the workshop. And I hope you've enjoyed it. And there's so much more you have to do now. What we were showing you are the basics. And it's up to you to see how far you can take it. And you can always get in touch with us and we will troubleshoot if there are any issues. So today, as we promised, we'll look into Astropy. And I'll share my screen. Yeah. So we'll have a hands-on tutorial on Astropy. And I think Priya has already shared the notebooks with you. And so what is Astropy? Astropy project is a community effort to develop a single core package for astronomy in Python and foster interoperability between Python and astronomy packages. So like we mentioned to you, one thing you have to remember is that Python is an ocean. There are so many things and nobody can teach you everything, and you needn't learn everything when you start off. You learn as you go. Whatever you have to do, whatever you want to do, on that basis, you learn that aspect of Python and proceed with it. And as you have seen over these past few days, there's a lot of community support to train people and to help them, troubleshoot them, and go on. So it's impossible for anyone to know, in the earlier programming languages like Fortran, C, or whatever, probably you could understand the whole thing and then start off with it. But in Python, that's not what you do. Here you start off, and we have given you something very basic and fundamental how to go about. And then as you require a certain thing, you go on. So Python we have learned for the first 3 sessions. And today we'll be using Python specifically for astronomy. In fact, a part of it using Python for astronomy has already been done. We have seen the M3 globular cluster data, and we did some kind of plotting and some kind of statistical analysis. But here we have Astropy, and the name as it suggests, it's Python for astronomy. This has been developed by a lot of brilliant people, and it's there for us to use it. So there are Astropy packages structured into several submodules, and we will cover only a few, which will indicate how you can use it. So I will be looking into Astropy units, in particular the quantities, Astropy units quantities, and Astropy coordinates. And Priya will do the Astropy tables, Astropy input-output, handling fits format, and plotting and visualizing these things. Okay, and obviously there are other associated packages. You can see the notebook which we have shared. And let me remind you that this has been adapted from tutorial by Alex Donat. And we have just adapted for this tutorial. And the best way of learning Python is to work as we proceed. And there are various resources which are right here. And the moment you click on these, it will connect you to the web page and it will take you to those resources. Okay. So as you have seen, this the setting up, you have to set the environment to be doing things in Python, and I'm importing matplotlib as .pyplot as PLT. This is what Priya had done in her session, and you have this statement, this percentage sign with matplotlib inline, and you can run it even without doing this, but it's better to put that command so that as you are plotting, you will keep getting it. So we are setting up the environment. So I have imported matplotlib, and now I'll import NumPy as NP and import Astropy. Okay. So as we have mentioned, obviously you can import NumPy as anything you like. You can call it XX, but it's slightly absurd to be doing that because there's a convention which people use, and your code has to be readable for you and for others when they reuse it. So it's better to stick to this, but basically we are creating an alias by saying import NumPy as NP so that we needn't write NumPy all the time. We can just use NP instead, right? So similarly, we could have imported Astropy as some ASTR, and then we could have used it, but fine. I have put hash to these commands. If you want to see what version of NumPy you have, you can run it with that, and you will see that your NumPy version is on my system, it is 1.20.3. And similarly, Astropy version, we can see by running this print astropy.version, right? So the Astropy version which is installed in my system is 4.3.1. Okay, now coming to the basic units and quantities. Many of you who are already into astronomy, you know that we use various units in astronomy. The AU, astronomical unit, AU, which is the distance between sun and earth. Then we have light year, which is the distance traveled by light in 1 year. And then we have this parsec, kiloparsecs, megaparsecs, and so on. So the parsec is 3.26 light years. Okay, so we will first import the units. Yeah, so from Astropy, import units as U. Yeah, I hope you are doing it as we proceed. And obviously there's no output. Yeah, it is imported as U. And then I if I say distance is equal to 1 point, and I put, say, when I multiply it by U dot light year. Yeah, so in Astropy, there is something called light year defined, and we are getting the value of light year by typing U dot light year. Similarly, we'll have U dot parsec and so on. So what we are doing here is I am taking U light year and I am storing it into the distance, the variable called distance. Okay, and if I print this variable distance now, it will show me that it is 1 light year. Okay. So now if I want to convert this distance to meters, 1 light year, how many meters is 1 light year? So there is this, I am using the distance dot to the function called distance here. So the variable which you have defined distance and 2, and in this I write meters. yeah, meter. And when you run, you'll see that the distance to 1 light year is 9.460735 to the power of 15 meters, right? This is very simple for us to convert from light years to meters and so on and so forth. Okay, so I can even try another thing called, say, distance to parsecs. Distance, what is the distance? Distance is the variable, and I say distance to, and I'm doing it to parsec. So parsec is defined in the Astropy, and I say parsec. Yeah, distance to parsec. And in parsecs, 1 light year is 0.306619 parsecs. Okay, so this is the way you can convert these, and then you can find out the type. If you want to find out what is the type of this distance, yeah, something which we have used, and it is showing that it's Astropy units, quantities. Okay, and I can also check. Yeah, and if I use this distance unit, it shows me that the distance, that variable distance which we have defined, is in light years, right? So you can convert these from one to the other, and so on. And now, if I suppose I multiply distance by, say, 10, and it would become 10 light years. Okay. Got it? Now, if I further suppose I define something, I can define a variable called distances. Okay. And I'm using the list which we had done earlier. And I say 1, 4, and 7. Yeah, and you can create a list of whatever size. And if I execute this, and if you look at what this distances is, yeah, there's a difference between distance and distances, two variables we have defined, and it is showing you it is 147, right? These are the distances. And suppose I define something called distances, dists, and I call it, I say it is, sorry, I take distances and I multiply it by, say, 10, and I print what this dist is. Distances, and you will see that it is creating this kind of a, yeah, you have seen how list gets replicated, isn't it? Yeah. And now, if I define, say, this distances, say, I'll use another variable called with capital, say, distances, say 2, and I take distances and I multiply it by u dot light year. Yeah, and if I print this. Distance just 2, and I print it, you will see that I have this 127, and now I have converted into light years, right? So this is the way you can use your units. And yeah, so now suppose I run the command, the np.max of distances. I want to find out the max of that. See, we had distances was 147, and np.numpy.max, we are using the max function from npy. And when we are checking out on the distances, it's giving me the maximum one there in the list. And similarly, when we say, if you say min of distances, you will get 1 there. And similarly, you can say I say mean of it. I want to calculate the mean, and you get the average of the mean of that, right? So what was distances? Distances was 147, and maximum was giving us 7, minimum was giving us 1, and the average was 8, because 1 plus 4 plus 7 divided by 3, and there you get it, right? So there are all these functions which you can find out of these values, right? So you can, this is just to illustrate some basic ones. And now, suppose we have, so you have to be careful about a few things. Say, for example, I take np.log of 30, and we have certain MEVs, and I run it, it's going to give me some kind of an error, because this log function wants it to be without a dimensionless. Yeah, it has to be dimensional. So there are certain quantities which have to be dimensionless. So for this to be functioning fine, you have to make it a dimensionless quantity. And what I do is I just divide it by, I'm dividing it by 10 star U MEV. So we are getting rid of these units. And now when we run this, we will get what the log of 30 in MEVs, log of 30, because we did not want it this has to be, the log has to be you have to feed in a dimensionless quantity. Okay, so this is how we handle. And suppose we want to look at speed of light, which is distance by, distance was 1 light year. We are calculating the speed of light. So the variable distance which we had was 1 light year. And the time unit which you are using is u dot year. And we'll print what it is, and we get the speed of light as this. Right? So this is how you can find. And similarly, if you want to find out the speed of light, you can find speed of light in we are converting the speed of light to angstroms per day and printing it. So we are getting it in angstroms per day, right? So this is how you can convert very conveniently from one unit system to another and so on and so forth. Right. And now that we have defined what the speed of light is, yeah, so if I do speed underscore of underscore light, yeah, this is my variable, and I want to see it in the SI units. I get it in the SI units, and the same thing if I want it in CGS units, if I want to convert it to CGHS units, and your guess is right, you just have to write CGS, and it will give you in centimeters per second, right? So it makes things so simple and easy for us to convert from one to another and so on and so forth, right? Similarly, in astronomy, you use, there are various physical quantities and they are measured in different units. You know, most of the time we write temperature in terms of Celsius or in Fahrenheit, but in astronomy, we do it in Kelvin. So suppose we want to convert, say we have temperature. We have temperature, which is say 75 degrees in what units? I say units and I say Celsius, right? I have temperature in Celsius, right? And I want to convert this temperature into Kelvin. Yeah, so temperature to Kelvin. Again, see the function, the way you operate is the same thing. The variable name dot to, and then you put, see, for example, we had meters there, and now we are converting into Kelvin, and equivalencies of this U temperature which we had. So once you run that, you will get the same temperature. 75 degrees Celsius is 348 Kelvin, right? Right, and you can convert it back from one form to another. And suppose I take minus 273 Celsius, we are getting it in Kelvin as 0.05 Kelvin, right? So it's very simple to convert from one to another and so on. Okay, so yeah. So we have the main file which we have shared with you. You have more of these miscellaneous ones. Just to indicate to you, Astropy provides a lot of inbuilt physical and astronomical constants, and which can be used. And you can see the hyperlink here, astropy.constants. So if you click on that, you will see all the possible constants which are available. Okay. And to illustrate, what you need to do is you have to, again, from Astropy, import constants as constants, right? And there are different constants which are available. For example, the speed of light, parsecs, we have already seen, mass of Earth, mass of Jupiter, mass of Sun, various things are already there. And I print the constant C2 kilometers per second And the speed of light, the c which you see is the speed of light which is stored as the constant, Astropy constants. And if you are converting into kilometers per second, this is how you get it. And if you want to convert it to meters per second, then you write meters per second and you will get it to that. Okay, so similarly, you can write a function that can make sure the input given are in the right units using Astropy quantities input. For example, you have this code here. And for black body radiation, we have this frequency and temperature. They are in hertz and temperatures in Kelvin. You specify it here. And then you feed it into this function which we are defining black body. And see, you get it here. And if I run this code, you will see you are getting an error because the units are not compatible. So you have to get it in the right one, because our quantity which we have defined has to be in hertz, right? So the first line of code which I ran, you notice this one is the unit is in nanometers, right? But we want it in hertz, right? So instead of, if we had written this as hertz and we had run it, then we would have got the value for this, right? So it's important to convert, to use the right units, and to do it in Astropy, it is pretty simple. Okay, so this is something very basic of basics of our units, and let's move on to the next aspect. There are certain exercises here. Yeah, I will not give you this performance tips option here. This is there available into your in your system, but basically it shows you how you can use different functions, whether you can use .u kilometers or u units and do it, the speed of computation, how it changes. Yeah, so you can check it out with the Python notebook which has been provided to you. Instead, we will move on to the next aspect, which is the coordinate systems. And yeah, so let me share just for a small recap for the people who are not into astronomy, just 1 or 2 slides on this. The coordinate systems which we use in astronomy, as you know, are either the horizontal coordinate system, where you use alt-azimuth. So if the observer is at the center of the celestial sphere around, the point overhead is a zenith, and you have if you have a pole star somewhere here, you draw a great circle from zenith meeting to the horizon. Yeah, so the axis from observer to the point directly overhead. Yeah, so if I am the observer, I am right at the center and the point overhead is the zenith. And if pole star is sitting at a certain point here, I draw a great circle and meet the horizon. So what is the horizon? We have zenith to observer and a plane which is perpendicular to this, which extends to meet the celestial equator, is called the horizon. Yeah, and so the point where the great circle meets the zenith, Polaris meets the horizon, that's the north point. And the point right opposite is south. East is 90 degrees on your right, and west is 90 degrees to your left. So that gives us our things, and we use the horizon as the reference plane. So if you are looking at any object, any star or an object here, you draw a great circle from zenith, star and meet the horizon, and the angle which that object makes with the horizon. I'll switch on the camera again. And so if this is a horizon and the angle which it makes above the horizon, whatever object you are seeing, this is called the altitude above the horizon. And from the north seeking point, you measure this angle, which gives you the azimuth. So this is a local coordinate system, alt-azimuth system, which is good only when used very locally. But obviously, every object we observe, say, what I observed from Hyderabad, India, the alt-azimuth of a certain object at a given time right here will be very different for somebody who's sitting in Paris or in Moscow or in Russia, because your horizon varies as you go from one location to another, since our Earth is a sphere. If Earth was flat, then this wouldn't have happened. So the other one which is most usually used, which is a better one for astronomers, is where you use right ascension and declination, RA and dec. And in this, you, instead of taking observer to the zenith as an axis of reference and a plane perpendicular to the horizontal plane as a reference plane, rather we use the observer to the pole star as the axis of interest, and we take a plane which bisects this axis as 90 degrees, and we extend that to meet the celestial sphere, and this is called the celestial equator. So the angle which that object makes from the celestial equator, right? This angle is called the declination. And for the other coordinate, the plane where the ecliptic and the celestial equator intersect, it is called the first point of Aries. And that is the angle which you see in this, from this first point of Aries to wherever you have projected the star in the horizon. This gives you the RA, right ascension. So right in ascension and declination are more universal. Any object, any observer from any part of the world would have the same right ascension and declination for any star or and so on. Okay. And there's yet another one where you use the apparent orbital plane of the sun, which is called the ecliptic. And you measure the same way ecliptic longitude and latitude as we do on Earth, as we have done it for all the other coordinate systems. But here the reference plane is that of the ecliptic plane. So you have the ecliptic longitude and latitude. Another one, when we are looking at from the perspective of our galaxy, you know, our Milky Way galaxy has a beautiful barred spiral structure, and our sun is not at the center of our Milky Way galaxy, but it is some 28 kiloparsecs from the center. And we use the galactic plane as a reference plane. So you measure what are the angles above the plane with sun as your point of observation. You measure, if you are measuring this object here, you see what is the angle above the galactic plane. This is called the galactic latitude. And the longitude is measured in the galactic plane. If you look towards the center of our galaxy, we have 0 longitude. And as you move, you get 25, 30, 90, and so on, and 360 back to this. So we have the galactic coordinates. Okay, so these are the coordinate systems which we use. And yeah, and Astropy has your sky coordinates Yeah, and we do this from astropy.coordinates, import sky coordinates. Okay, so you run it, and it can be created by passing a position, angle for longitude and latitude, and a keyword to specify a coordinate frame. Right, so for example, I have this position for the Crab Nebula, and we have imported this sky coordinates, and sky coordinate is a function in which you specify the longitude and the latitude, and you specify what frame you are looking at. Okay, so so it has got the and I will print what this position is. So I write position for this crab, right? So if I print it, I'm getting this sky coordinates. So this ICRS is giving us in RA and declination, and it is giving that. So it's storing the location of this variable, which I'm calling it crab, as so these values are taken from the net, yeah, right ascension and declination of the Crab Nebula, and I'm using this ICRS so right ascension and declination. So these values are now stored in right ascension and declination, and similarly, you can have for more objects. Yes, you can give a list. Yeah, I'm giving many positions in one row. In this case, I'm giving 2, but I can give many more. So in this rectangular bracket, I'm giving 345 and 234.3 the array, and declinations I'm giving for 2 objects, minus 0.1 and 0. And we are specifying that these are in degrees. So unit which we are using is in degrees. And this time I'm using, I'm saying these are galactic coordinates, right? And then I'm printing the position. So it is giving now in terms of this L and B, galactic longitude and galactic latitude. Okay, so and we have got and these positions which we have, it has for 2 objects. That's why we have we have 2 here. Yeah, so for the first you have 35, 345, and RA and DEC we have these 2, and for the second object we have these 2, right? So this is the way we can do it, and so now we have this position crab, which we have defined here. And we are writing it in terms of hours, minutes, and seconds, right? And we'll see that now if you write this position, yeah, so let me comment one of this, and I will write the positions now. Yeah. So I'm getting this crab now see, we had written it in 5 hours, 34 minutes, and so on, so many seconds. And we are converting it into the in degrees, right? Like, so we are getting back the degrees which we had 83 degrees, and you can convert. So you have this RA deck can be written in terms of degrees, or you can write it in terms of hours, minutes, and yeah. So you units, hours, degrees, or we are writing it in this. Okay, so this and you can get the position in galactic coordinate system, and yeah, so now I'm getting the same position crab which we have. We are converting it to the galactic one, and we're using this function transform to, and here you specify whichever one you want. Okay, and when you run it, and I write what the was in gal is, in galactic coordinates, I'm getting it in the galactic coordinate system, which is 184.5 and minus 5.7. Okay, so this is the way you can convert very conveniently from one to another. And again, yeah. So there are various ways you can do that by using various inbuilt ones. So alternative ways, you can say position underscore crab in ICRS, right? Or I could say position of crab in longitude. Yeah, and you can convert from one to another, and so on and so forth. Similarly, if I say latitude, I just want to get what the latitude is, I'll get only the latitude of that. Okay, so there are all these very convenient things to use, and yeah. So now, yeah. So now we will look at say this finding distances between two positions in Astropy. Yeah, so coming to this. So we are defining this variable positions of Sagittarius, and in sky coordinates, in the galactic frame, if you're using the galactic frame, then the Sagittarius A, as you know, is 0, 0, right? So our galactic center is at Sagittarius, so our longitude is 0, and it is lying in the plane. That's why it's galactic longitude, latitude, both are 0. So we are defining this position Sagittarius as this. And now if I run it, we are getting the separation of crab, right? So position crab was the position of crab which we had defined earlier. And if I want to find out the distance of that from this position which we have defined, right? We have two positions defined. And when you, right? So it's very simple. You just have separation, and you have these two variables. Position crab dot separation and position the Sagittarius. And this is what it gives you. So if you recall, the position crab was 83.6 and 22.4. in RA index. So this one, the first one which you see is in galactic, and the second one is the finally when we had run position crab, we had run it in RA deck, so it was stored as RA deck. Yeah. Yeah. Right. So okay. So right. So we have looked at this. Now coming to our last aspect, this alt-azimuth coordinate system, which is the from Earth location. So you have to, yeah. So suppose you are planning some observations. It can be useful for us to transform the sky coordinates into the horizontal coordinate system. And what this will tell you is if you see that it is above the horizon or not, yeah, whether your altitude is a positive one or not, or at what angle it is. If it's at 10 degrees or 20 degrees above the horizon, then it's not a good time to observe. So if you want to find out that a particular object you want to observe from a particular location on Earth, then how do we plan our calculations, right? So we have to use this not so good but alt-azimuth system because it's a convenient one. And it will very conveniently tell us at where to see it in our local sky, because it's very easy to find altitude from the horizon easily. And even the azimuth from, you exactly know where the north point is and very easily you can find out. Yeah. So we from astropy.coordinates, we import Earth location and alt as, right? And from astropy time, yeah. So you have astropy coordinates. In that you have Earth location as well as alt azimuth. And in time, you import, we are importing time. Okay. So we define some Earth location. Suppose I'm looking at some place, say for example, Moscow. Yeah. So Moscow, and we have got this Earth location function from astropy coordinates, and it works this way. You have latitude equal to, you can find out the latitude of Moscow from the net or whichever location you are at the moment, and you are getting it in, if you are got it in degrees, yeah, like we have got it here. You can have two formats in which you can get it, either in terms of hour angle and so on and so forth, or in units of 55 degrees, and longitude also is 37.67 degrees. Yes, so we specified what are the degrees. That's why we are multiplying it with these. And so you have set your location as latitude, longitude 37.61 and latitude as 55.75. If there's somebody logged in from Russia, maybe they can check whether these things are right. And so print Moscow geodesic, and it is giving you all these details. Okay, and now if you say now what is the time? So this time we have exported, and we say time now. Okay. And if you want to see what the time is, I'll print this now here. And it's giving you the time of the object. The scale is UTC. And the value is, we have 12 November 2021 and 13 hours, 19 minutes. And so it's somewhere in the afternoon, 1:19.2. Yeah, this is the time in Moscow at this moment. Okay. So you see how beautiful and simple it is. And now you can use this alt-azimuth. You define a variable, say alt-azimuth, and alt-as, which we have got here. We have imported alt-as, and observation time is now. You specify what time you want, and the location we have is Moscow. We have stored this. Yeah, Moscow is something which we have. Yeah, this is a variable name. Yeah, so I'm putting that here, and I want to see how is that crab alt-azimuth is at this time. Where is, yes, that crab which we had, and we will print this. Print crab alt-azimuth. Okay. Okay, so here it's showing us that observation time, which is now. We wanted to check what it is at this time, and this is the time. You can change this time to whatever time you require, so many hours from now. But since we are doing it with this time, we are getting at this time, what is the location? This is the location. Yeah, and it is showing you the temperature in degrees, relative humidity, various things, and it is showing you where it is. Okay, so this will help us decide whether it is good time to see. And what we are seeing is it is at 23.75 alt-azimuth. The altitude is 23.75. Azimuth is 23.75 and altitude is minus 9.275. So this indicates this is below the horizon. So it is not right time for us to observe this object, this crab which we are looking at. So yeah, and anyway it is afternoon. So unless you are using radio observations, you can do that. Yeah. So if it was above the horizon and if you change the time to some other, or I can change my location. I can change my location to, say, 78 degrees. I will not change the variable name to Moscow, but Hyderabad is at 78 and 17.5, roughly. And I'll continue to call it Moscow, let's not write Hyderabad and so on. And time now, which we have is same date. Latitude. Long is the other way around. No? Latitude is 17 and longitude is 78. Yeah. So this is our roughly where we are stationed right now. And time now is anyway, in short, from this location, we'll see what is happening. And you see that it is minus 12.94. And, yeah, azimuth is 61.46. And this thing is, yeah. So there are some exercises which we will be giving, and this written right here. There is one easy one and there is an expert one. So go for both and I'm sure you'll be able to do it. So with this, I will stop my presentation, and if there are any questions or so we can try to answer, or Priya will now continue and she will handle the other aspects, which is essentially she will looking into how to read, write fits files and read images, and yeah, she'll be looking at Astropy tables, Astropy fits format, and so on. So, okay, so if there are any questions,
We just wait for some questions. These were the questions or the.
Are there any questions? Yeah, so in fact, we wanted to express our sincere, what do you call, appreciation that we have conducted various online workshops, but this group is extremely well organized, well behaved. There's not much of crosstalk or irrelevant discussions. Only when they need, in a very good way, they put it up in the chat box. Otherwise, many people create. Yeah, so there is confusion between MEV conversion and between code. Yeah. Yeah. So yeah. So basically, there is a question from Vara Chamani, and yeah. So the what I wanted to show is that there are some of the functions, for example, log, which we were using, log function which we were using, it had to be dimensionless. So first I ran it with certain dimensions, and then that gives you an error because that log function requires a numeric value without dimensions, not kilometers per second, not MEVs, not parsecs, right? It requires a numeric value. And for such functions, you have to be a bit careful and see if it is a dimensionless input which is required, then you remove the dimension. And that's what we did by dividing it by the units of MEVs, right? And that's what it was. So
So all the materials on Slack as Telegram. So please have a look. Yeah, how many Telegram as that? So it's all great. I think we'll take 2 minutes for a break time. Take a break now, and then I'll start after the break. So we take a 10-minute break. And meanwhile, we are anyway logged in and online. So if people have any questions, you're most welcome to ask those questions. You can unmute yourself or you can use the chat box. Right? But otherwise, for the others, you can have a break, you can go and kick off.
All right, so we are going to have a short break now, and we will be meeting after 10 minutes.
Hello. I just said that we'll take a break now because it has a regular break timing, right? We'll take our break and it's for 10 minutes. And if people have doubts, they can ask it. If you all want it to be shared over email also, we can do it, but the files are a little large. So, but we can do that. So what we'll do is we'll share all the bundles later, right? For each day. So I'll bundle it all together and then we'll share it. Yeah. So let's break for 10 minutes and we'll meet in 10 minutes. Bye. Thanks, everyone. Thanks for your kind comments. But I would urge you all, which Mamta will also tell you, that please fill the feedback forms, right? And please write all these kind, nice words which you have in that, because that's what we're going to use so that we, plan our future events. We need to know what is the feedback, what would like, right? So that we can do that for you. So my request to you all would be, is thanks for all the compliments, but please put it on the feedback form so that it gets registered, right? And I'll start in a minute. So hello everyone, and I'm back. So we are going to continue with the Astropy stuff that we were talking about. And Asansa covered with you all two parts. One was the units, and the second thing was about the coordinates, which are very important aspects in astronomy, right? These are things we need very essentially. And then I'm going to continue with some more stuff. And one is on tables and the other part is on basic images. So you'll already seen that in astronomy, we are basically dealing with data which is in tables, catalogs, right? Like the CSV files and the other files which we were plotting with Matplotlib or with Series-1, etc. So you actually, tables is a very convenient way of handling data. In principle, you could also handle it with pandas or other software like we've mentioned earlier. There's not one way of doing things. You can choose the one that suits you and which one you like more, right? But what we want to highlight, what I want to highlight is what is the difference and what is the advantage of using tables, right? So the first important thing is obviously you import the package of tables. And so you say from Astropy table, import table. And here I've left this on. So we are generating our table. What is our table? Our table is essentially, so I'm going to define my table, okay, as a table, okay, and now we are adding, so this is a table has been made, and now we are adding columns to the table. So I've already written this, so I don't need to type it in your presence. Essentially what you see is that, if I'll show it to you, is I'm basically just giving you a table of 4 objects. I'm going to show it to you over here. Oh, I didn't run this, sorry. So I'll run this. U is not defined. What is not defined? 1 minute, I'll just do this again. Do this again. And probably all my import statements, I should do that again. Let me just run all above. I'll run everything. Yeah, the import statements and all have not been run. So I'll just run them again. And hopefully now it will come. Yep. So now if you see, if you look at the table, this is the table. So what is the table? The table basically has 4 objects. One is Crab, one is Sagittarius A star, there's Cassiopeia A and Vela Junior. Okay. And if you look for each of these 4 objects, I have longitude, I have latitude and a source class. And like sir already mentioned to you, the advantage in Astropy is that with every object you have a thing attached to it, which is called its unit, right? So with your data, you have it attached, it comes bundled with it. So here it's already bundled that these are in degrees. You can see over here, how do we know that? Because we've written udeg, right? Over here, you've written u.deg. So from the beginning only, we have defined that longitude and latitude is in units of degrees, right? And therefore, it gets associated to the table. And here it's telling you the type. What type of variable is there? So the name of this object is a string which has length 11, right? That's for the names Crab, Sage, Cassiopeia, Vela, etc. That goes for the name. Longitude and latitude, these are floats, right? And source class is again a string. So the source class is actually telling you what kind of an object it is, right? For example, Cassiopeia and Vela, these are supernova remnants. Crab is the Crab Nebula, which has the pulsar in it. So in short, this is a very simple table where you had all this. But the advantage is that the information is already sitting with the table about what are the units, etc., of these objects, right? So that's our table. Now, how could we access rows and things like that of it? So for example, I can, this is very similar to what we did, for example, in NumPy, right? So I can say, for example, I can list the column names, right? And the column names, as you know, is source name, galactic longitude, galactic latitude, source class, right? That's what we defined when we defined the table. So you see, when we defined the table, we actually gave, this was the left-hand side, what was the column, and we gave the whole thing listing over there, right? So that's what's our column names. Now, if I want to know what is there in the list of, I want to list a particular single column, I can say, sorry, I'll put table, and I can say, I want to specifically look for the column which is called glon, and here you can see, I'm sorry, this is here, and here you can see I'm specifically looking at what is listed under the galactic longitude list, the column. So that is my this thing. I can also look for, if I don't want only galactic longitude, I could also look for source name or pick up whichever columns I like, right? So I'm going to do this. I can take galactic longitude, and I can, for example, take, we have called it, the first column was called source name, and that's it. So I am now listing, 1 minute, I have spelt it wrongly. Source name, oh sorry, I put 2 inverted commas here. So this is this, right? So this is my source name in galactic. What is the syntax wrong? Source name, oh god, sorry, I put 2 over here too. Yeah, so here it's listing to me these 2 columns which I had in my data, which is this, right? Now, I can also, for example, if you remember, we also, you can get, if you remember, one factor which we had was units. The other thing is what is called quantity, right? So you can actually look for this, so there are properties to things. One property is the unit, one property is the quantity. So I can also look for what is the quantity for this thing. For example, if I take it for galactic longitude, I can put it and I can see the quantity which I have for this, which is over here, right? And I run this thing, and here I can see these quantities. So here, what is this? This is again giving me, if you remember in longitudes, the first value is 184. Sagittarius A, since it's the center of the galaxy, its LB values both are 0. That's here. Cassiopeia is here, and Vela Junior is here, right? So this is giving me the longitudes of all my quantities, right? I can exactly like we did it in NumPy, we can even slice it. For example, I can take table and I say take it from 0 to 2. So it's going to take me, it's going to give me the first thing and the second thing. So it's only going to give me 2 objects, which is Crab and Sagittarius. If you remember when we did slicing in NumPy, 2 is not counted. So the index which will come is only 0 and 1. It does not include 2. So this is 0 was Crab, and the second one is Sagittarius. So you're getting this, right? Similarly, you can even do selections. If I want to select a particular thing in this, right, I can do a selection of table where I choose, I can select it in such a way. This depends on your requirement. You may need to do such a thing. So I may select it that I want to specifically pick up the one which has source name equal to Crab, right? I only want the data on source name equal to Crab. And hence I select from the table, and I will look over here. I can, if I want to see what is the result, I have to do table, and I will say the selection, because selection is what, this one is the index of, this is the index of the row in the table which has the source name called Crab. So selection will give me that. Table selection will give me that line itself, right? So if you see over here, I can put selection. So selection, what you see is nothing but it is the index, right? Which is the one which gives me the value for grab. Now there are many more ways of actually doing the indexing with thing, but you can see it's explained over here. You can click on this. You all have this. I've given you all the notebook. So if you click on it, you will get the link. It actually tells you how do you create more indexes or whatever, depending on that. Now these are useful things if you want to specifically pick up certain parameters in your, in your file or something. You want it, then you will have to do this thing. Now let's see. Now, if you remember yesterday we spoke about reading tables. What if you want to write tables? Now in table, what's very nice is that table has a function called write, right? And the good thing about table write is you don't have to, you just have to give the extension of the file. So for example, I can just say table write, and I can say, for example, example.fits, supposing, right? I can say example.fits, and yeah, I'm going to say the format is equal to fits format, right? And you will see in your working directory, example, what is this? Oh, sorry, example.fits has to be in inverted commas. Yeah. So table, this is doing it of that. So now what is it done? It has made it as a example.fits file. I can also copy it in a different format. If you remember, we did comma separated variables, but there exists in Astropy another this thing which is called eCSV. It's like an extended CSV. Okay, and the format is called ASCII.eCSV, right? This is the thing. Now, what is the advantage of this? I can show it to you. Example.eCSV is that this is like a CSV file, comma separated variable, but it has an additional set of metadata. Okay, so we will not read it like this. We will have to read it as not like this, but it will have to be done as table read. Also in inverted commas. Okay, so now you see that this is a normal CSV file. Other than that, it also has additional information, which is the information about the material that is there, right? So it has what is called extended data about it. Okay, so this is the eCSV format. So what happens is you can write and read a table directly with this. If you remember when we did it with what did we do it with yesterday? We did it when we were reading the thing. We had to use a function called read_CSV, right? In this case, the function is table read, and you can read it like that, right? Similarly, so in short, you can create your own fits file or your own CSV file and take it like this, right? Write it as well as read it. Okay. Similarly, if you had an existing CSV file, you just say table read and you can import your CSV file, right? So supposing you had downloaded some data, like we asked you to download data, that CSV file can be there and you can read it, and it will read it. And you can see there are different formats in which it reads. You can see it over here. Essentially, almost most formats get read in this. So I can click on this and I can show you this, and you can see that there are a whole bunch of formats which it will read. So this will read formats including this, pandas, tables, etc. And all these things you will put the extended, what do you say, the extension of the file, CSV, then the enhanced CSV, various other formats, it will read it, right? So that makes it very easy for to use tables also to read or write CSV files. This is, we did another method earlier. Today we are seeing another method, right? Now, now what we are going to see is indexing and grouping. This is also a very interesting thing. You can actually index your, you can add an index. So for example, I can say table add index, right? And I can say specifically I add index for the call names. We've already done this for source names, source name, right? I'm sorry, I think this has to come as name. Oh, sorry, this bracket closes. Yeah. And now you can actually, if you want to know the location of it, you can do table.log, right? The location, and you can do it and with, for example, with Cassie. That was one of our source names. I think the Cassie has a space. Like this. Okay. Now another very good thing, which is very nice, is it can group. It can group things, right? And the grouping is very nice. For example, I can even, for example, here you see I've taken location which has Cassie. I can even take location, for example, which has Cassie, as well as, for example, crab, right? So I can take Cassie, I can take crab. What's wrong with this? Okay. So I have to add another square. Oh, sorry. Within it, I'm adding that, and hence I got to put one more bracket. Right, so this is the one which has both. Right, now what happens is, another very interesting thing which can be done with tables is you can group things. If you remember, we had put the types, right? Supernova, remnant, etc. So I can even ask the table to get grouped based on that factor, right? So I can say table grouped is a new variable, which is table dot group, and I say group by what? So I can say group underscore by, for example, if you remember, we had defined something called source class, right? I'll just show you the source class. If you remember over here, this was our source class, right? Which tells you what kind of a source it is. So for example, here you can pick this can be anything, right? For example, when we took that tips example, it could be gender, right? So you group them as per gender, male, female, etc. Or whatever other factor you want to use, you can use it. So I'm now saying group my data based on source class. And now you can see table grouped is equal to table grouped by square brackets are there. Round brackets. Okay. Sorry. I need to square round brackets. So you got to be very careful about the syntax, otherwise it won't work. Yeah. No, there's still a problem. So I have table grouped and table dot. I'll just add gaps in case that makes a difference. Table group by class, is it source class? Sorry, yeah. If you remember, this is a string, right? So it needs exactly the same name. So what it's now doing is it's going to group it based on the source class, right? And I'm now going to print. Let us see what does it do. So what I'm going to say is I can add a loop where I can say there are groups made in it. So I can say for group in the upper thing, which I have table grouped, right? Dot groups. Yeah. I'm going to ask it to print. So I will print group, and I want it on different lines. So I'm putting a slash here, right? So I'm doing it like this. Now just see, this is really beautiful. What it's done is it has grouped this thing. One group is the PWN, which is the crab, the pulsar. Then you see the supernova remnants are both grouped together in one group with Cassia and Vela. And then Sagittarius A is in a third group called UNC. So for example, if you had your catalog, and in your catalog you had, supposing, put some tag to each object. Okay, this one is a star, this is a galaxy. For example, you'll see it often that sometimes you have a catalog of a certain part of the sky, right? We don't have time to cover that this time, but if you get a catalog of a particular part of the sky, it may be the class is already defined, right? It says, for example, that there are galaxies over there, there are stars over there, there are quasars over there, whatever kind of objects they are. And you can actually make groups of those based on the class. So then you can make a separate listing of, for example, the stars of the catalog, the galaxies of the catalog, the quasars in the catalog, or whatever other kind of objects you're looking for, right? And therefore you can actually get it in that kind of a way, right? And these groups also by itself are tables, right? So what, supposing if I want to even say what is the type of my group, I can write type and I can say group, and here it is. So you can say it's an Astropy table, right? So it comes with these multiple things because these are the what do you say, the additional properties which you have of them, right? Now miscellaneous, I can show you of the, obviously there are simple commands. For example, you can do a table sort, right? So supposing if we want to sort our table on the basis of galactic longitude, right? I have to copy exactly LON in caps. I can sort it. So then it's going to sort it with table, this thing. And then I can view my table and you can see that here it has sorted it in terms of galactic longitudes, right? So you have 0 and then you have 111, 184, 266. So it has sorted it based on that, right? And similarly, you can group, you can sort. If you want to remove a certain row, right? So I can say, for example, for row in table, yeah. So I'm choosing a row in the table. I can say print. Okay, specifically if I want to do this, I will, a print always has to have a round bracket after it. So I will put the round and then I can say row. I'm going to only print the source names, for example. So the source name. And here you see, I'm only seeing the source name. Now there's another interesting thing which can be done with tables, which is, for example, if you want to see the table in a browser mode, you can actually say table show in browser, right? And you will see, you can put this as the JS viewer. Now you will see that this works out very nicely. Sorry, where is my mistake? Table show in browser. Oh, sorry, this is not equal to. Yeah. So here what you see, I can see the table in my browser. Okay. For example, you'll see the next and last. In case your table is very long, you'll be able to see the next, last, etc. But obviously this works out well if your table is, okay, not too long. If it is too long, then it's going to run into many pages. But if you want to have, a nice look at it to see what it's looking like, it's a good idea to have a look at it in the browser, right? So you can immediately, if you want to check out something, you can do that in the browser and look at your thing over there. So there are some exercises, like we said, that we've taken this tutorial from somebody else's, and he put them in these 3 forms. There are easy, there's advanced, and there's expert. So first one is add columns of array deck coordinates of objects in the example table. How would you add it, right? You already know NumPy. You can actually do those kind of things. Now in this data set which I have given you, it's already provided to you. You have a data set which is a catalog. Find the brightest source, right? You'll already know how to sort it. So you can look for which is the column which has the brightness, sort it and find the first one. So it will be with index 0 and that will be will give you that, right? So this would give you all the bright object. And you can try the expert exercise also, which is make an all sky plot of all the sources in this very catalog grouped by this. The class is mentioned, so you can make groups based on the source class and plot this thing in the form of, if you remember this projection we had written as WCS, there are different ways of projecting coordinates. So where is WCS? It was there, or here somewhere. Projection. You have to just change the projection to the one that they have mentioned, the Edkov projection, right? So try out these exercises and I'm sure that will be nice to do. I need to hurry up and I'm going to go on to the other important thing in astronomy, which we have is images, right? We have images. How do we deal with images? So what do? There is this thing which is Astropy input output IO. From input output, we are specifically going to deal with the package called FITS. And the FITS, okay. So not imports, but import, right? So I've imported the FITS package, which is this. Now, FITS is the flexible image transport system, which is the standard system of handling images in astronomy. Okay. Now, in these images, one thing is you have an image. A digital image has X, Y coordinates and a count, and along with that, it actually has what is called a header. Now, nowadays, you can actually group images together. For example, if you have an image of the same object, say in 5 photometric bands, all of them can have the same name, but each of them have a different index kinds to it, right? So if there's an HDU list, so if you do FITS open, the file is sitting inside. I've given you all the set of files. There's a folder called data, and in data, there is a file which is called, it has a long name. It is called CASA underscore 0.5. So this is basically a Chandra image. Okay. So it is a Chandra image from 0.5 to 1.5 keV. Okay. It's a fixed image. .gz. I hope I've written it correctly. CASA underscore 0.5 to 1.5 keV. Fits GZ. Let's try it. Okay, great. It's good. So now if I want to know how many images are sitting in this, I can actually see HDO list info, and this is going to tell me how many of them I have. And you can see that it basically has only one image in it, which is the primary image. This is with index number 0, which is an image which has a dimension of 1024 by 1024 pixels, where each data value for each position is a 32-bit float, right? So this is the kind of data which it is there, right? And you can see that this is the file name called this and that. Okay. Now you know that this actually, there's an image sitting over here. So I can say my image, so my image HDU, header data unit, is equal to. So now what I'm going to call, I'm going to call a new thing called the image HDU, which is the primary header, primary image sitting in that thing. Okay. So from this HDO list, right, I am going to, I'm going to pick up that primary image, which is this one, right? This primary one, and I will pick up that, right? I'm going to just pick up that image, which is this 1024. Now, okay. Okay, I'll display this a little bit later. So I can actually see my image HDU data. So you can see that this is an array, right? This is, like I told you, a two-dimensional image is nothing but an array, and the array has these things, right? Now, what if I want to see this image? Let us try to see this image. We are once again going to use matplotlib. If you remember matplotlib, I will use PLT, and I'm going to use imshow, which is to show the image. And what is the image I want to show is this exact image, which is image HDU data. And I'll tell you what is origin. It's telling you where is the origin for this data set, whether it's going to be lower or upper. It can be different options. Sorry, origin. I will say this is lower. So you'll see that your XY is coming to the lower left. There are also what is called color maps. So this is CMAP. These are all artificial colors. You must remember that, for example, this is a Chandra data. So obviously, these are X-ray photons. So they don't have a color. We are artificially using a color map. So if you see, this data actually has an image from the range of 0.5 kilo electron volts to 1.5 kilo electron volts, right? So what is basically done is, depending on the energy of the photon, we give it a certain color, right? And that is the colors which you are seeing in this color map, right? Which is coming out in this image. You have to remember that, for example, in X-ray images, or even optical images, these are artificial colors. There are different color maps, okay? If you actually do Shift Tab, you'll see there are many different color maps. This one is this. There are many different kinds of color maps which you can take. For example, there's another color map called heat, right? So heat gives you another color map, and you can get, does it not have heat? I think, let's take gray. Is gray a color map? No. How come it doesn't have color map? Let's take Inferno only, okay? But in short, there are different kinds of color maps. You can check it and see. I don't know why that's not coming, but we can just check that. Please give me this thing. Okay. So in short, you can actually see different these things. This image also has very important information, which is called its header information. Like I told you, specifically in FITS format, we have something called a header. A header is very important data because it's telling you data about this image. Okay, what does it tell you about this image? That this image is an image of Cassiope, right? You remember the name of it was written Casa, but that was actually Cassiope. So this is the object Cassiopeia A, which is a supernova remnant. It's telling you the date of observations. It's telling you the units of the RA deck, etc. It's telling you what are the coordinates, etc. So the header is coupled with the image, which has the basic information about the image, right? Now headers can be in principle edited also. You can add things onto the header. If you want to add something onto the header, you can add things to the header. You can remove things from the header depending upon your use, right? And in that way, you can this thing. Another important thing in these images, for example, you look over here, is if you look at this image, this is in pixels, right? We said 1024 by 1024 pixels. But a very important thing is we need to map these pixels to coordinates in the sky, okay? And that is called the World Coordinate System, the WCS. So I don't want this to be in pixels. I want it to be in sky coordinates so that I can directly compare it to some other data sets or to whatever it is, right? Because pixels are going to be my local coordinates dealing with my specific detector, but I want to do it for in general, right? So what you have to do is, if we want to now convert this, we want to put this in WCS coordinates, you have to actually from astropy.wcs, you have to import something called WCS, okay, which is the World Coordinate System. It is this thing. So from Astropy, right? So from Astropy WCS, I import my WCS. And let me define my WCS. What is my WCS? That is defined as WCS. It is defined as WCS, and I can say image HDU header. And I will do. Let me print my WCS and right. So there's a mistake over here. Where is the mistake? WCS is WCS image underscore HDU dot header. Where is my mistake? Oh, it says WCS is not okay. I imported this thing. Okay, sorry. I should have imported this in caps. So I'll re-import it in caps. Otherwise, it doesn't know. See, often the error message itself is telling you where your mistakes lies. I put this in lowercase. That's why I didn't define it. And now it should work fine. So now you can see that these are giving you the keywords for the conversion, right? And what I'm now going to do is I'm going to convert my pixels to WCS. So I will use the same thing which I used earlier, which is sky quads from pixel. So what am I doing? From pixel, I'm converting it to WCS coordinates. So 0, 0, and I'll say WCS, right? Very good. So now what's it telling me? It's telling me the center of my image, or the 0, 0 value, is actually this value in RADEX, right? So it has converted my pixels to RADEX coordinates, right? And therefore, I can actually get, if I want to know what is the position of Cassiope, actually that's the position of Cassiope, which is given to me by this thing, which is 351.58. I can actually, again, I'm just going to do a small thing, which I'm going to take position CAS A, and I can do again sky coordinates. I can convert it again if I want to do, and I can convert it and put it in the, in the other format if I want it in hours, minutes, and seconds, right? So I can accordingly get that too. So I'm going to now put it over here in the other coordinates, that is 23 hours, 23 minutes, 27.94 seconds, and comma, and I'm going to move the mouse, plus 58 degrees, 48 minutes, and 42.4. Actually, I should just convert these frame. So the ICRS frame, right? And we can get this over here, right? So then I can just, now I can again have a look at what is my position of CAS A. So now I'm doing the reverse. I'm reversing it to pixels. Right? And so, yeah. So you can see that this is about the center of that image. If you remember, that image was 1024, 1024, right? So half of 1024 is approximately this, and that center part is, that is the part which has these coordinates. So here we've done the reverse. We have actually converted it back to pixels. So this 511, 511 is the center of that 1024, 1024 image which you had. This is the position of these coordinates in that, right? So you can do back and forth. This you're converting it from pixels to WCS, and here you're converting 2 pixels, right? So here you can see that you can try out this option to read the data, cut out the data, get a radial profile, etc., right? I also want to try doing this small thing. Okay, there's just a little bit left. So just hold on for a little while and we can do this. Another important, if you'll remember, we did subplots, right? So I can also define what I call axis, right? We did it when we did matplotlib. So I can put axis subplot, right? And here you see there is a thing of projection, right? And let me say this is WCS. And I can also, this is another way of showing the image. So this is AxImShow. This will work better for you if you're doing it with multiple plots, but I'm just showing you with one. So this is with image, HDO data, HDO.data. Again, I'm going to take the same CMAP, which is the Inferno one. And the origin is the X0, Y0 point, right? So, which is the lower one. If you take it upper, we'll just have a look, what does it do? Right, this is the lower one. And we can run this, which is over here. If you like, just like we did in matplotlib, you can also set labels. For example, I can say X, I can say set X label. Okay, and I can say it's array in deg, right? This is, sorry, it is not X comma, this is X dot set X label is this. I can run this, oops. Oh, sorry, this has to come in inverted commas. The label has to come in inverted commas. Oops. Yeah. So you see, I put the X label with array deg, and I can also put my Y label. So I'm going to cut paste this thing. I don't want to make new mistakes. So I'm going to just write deg, and I'll make this my Y label. So I can run this, and here you see I get my Y label excellent. Now, like I told you, origin is this lower. You can even see what happens if the origin went upper, right? So this X0, Y0 is going up over here. lower, yeah. So remember we tried gray with GRAY. Very good. So our color map problem is solved. We were wondering what happened. Gray is not GREY, it's GRAY. So I made this mistake. So very good. If we can change it to gray, right? Or whatever color, but I'm sure Inferno looks better. So you can change it according to that. You can also, if you want, you can even add a grid to this, right? So you can, for example, say ax dot grid, right? This is adding a grid to it. You can add the line width as per your liking. You can have a look at what are all the parameters which you can change. So let's say my line width is 0.3. Let me say I put a line style. Just to make it look different, I'm going to put a line style which is dashed lines. And maybe I can put a color. I can put a color, say let me put green, right? And when I run it, we can't see this. I think I'll change this color map. Green is not showing, it's too black. So I'll instead make this white only. White will show. Yeah, so you all can see these grid lines which are in this image. I am getting grid lines with which you can this thing. You can also add a cross mark at a certain position, right? Which will be your marker for where is Cassie, right? For example, see, these are all things just to beautify the image. You can just, they don't make a very big difference, but they obviously make your image looks better. So you'll say ax scatter, and I can say array deck transform. If you remember, now I've got to do this with this. So it is transform AX get transform, and we have, see, the syntax is a little cryptic, but we have to live with the syntax. So please, that's why we are giving you the notebooks, so that when you try it out yourself, you will exactly have a copy of what is the kind of syntax you need to use, right? Because like you already saw while I was also doing it, if you make a mistake in the syntax, the whole thing, it doesn't work. So be careful about the syntax. So I'm saying I have an X marker and I run this. If there's no mistake, I made a mistake. So what do I do? X scatter array deck. Is that, what is the problem? It is saying an array deck. Does it want? Okay. Array, I have not defined what is array and what is deck. So I will say array is equal to position of Cassie dot ICRS dot array in degrees, right? And similarly, now I have to define deck, right? So I will write this, and I will write deck is equal to position this thing, and here I'm going to put deck, and here I run this, and great. See, this is giving me a cross mark. This is the position of Cassie, right? The last thing I hope I have, yeah, I just do. There's a last thing which I can do is if you want to make a circle around this. Should I do it? It's there in your Python notebook. There are ways of actually getting a circle over here. So if you want to add a geometrical shape to this, I am going to slightly, okay. So what I'm going to try, I have the thing here with me. So I'm going to do something which is not very nice, but I'm just doing that so that we finish fast. And here is, how do I actually get a circle? So we already put the cross mark, and here you see if I want to put a circle, I will actually have to put all these commands. So here you can see there's matplotlib patches import circle. So you can run this, you'll get the circle, and you do this. And here, this part is there in your Python notebook, okay? So don't worry about the code, but essentially you are defining a circle which has a radius to some value, which has the edge color of white, and you're putting this. So with this, you can mark this object in your image, right? I didn't type because I thought if I type this, I'll make mistakes while typing. It will take very long. And we just have precious 7 minutes left. There are exercises also in this Python notebook. So please try these exercises. And I'll stop over here. I'll take questions. I can see there's some questions in the chat. And okay. So Anushka says, can you please explain a little bit about the image index value range and its significance? So image index value range is, like I told you, it is the, it is an XY grid, right? So the index is exactly how you define an index for a two-dimensional grid, right? Because the image is a two-dimensional thing. So you just have to pick it up like that. Anushka. Is that fine, or yeah, Anushka, is that fine with you? So that's why we did NumPy and all those things, because that is showing you why and how, how do you actually handle all these things, because that essentially is based on, these, I think I stopped the share. Okay, let me stop the share. Yeah. And are there any more questions? Thank you. Okay. So are there any more questions, or Mamta, do you want to say something?
Yes, I think.
Yeah, so one final thing is, we'll send you all a mail with all the things for all the weeks and the exercises. But in principle, till you receive that also, everything is already sitting in Slack or in Telegram. So you can definitely scroll up or down and you'll find everything, because every day we've been posting it properly on Slack as well as on Telegram. So even if you have a delay in getting the mail, please do search in your Slack this thing, you will find it all. Yeah, everything is there. Yeah. Mamta, you want to say something?
Yes. So I guess there are no more questions.
I don't see. I think maybe this became a real big shot.
Yeah, it was a bit quick, but it was, again, as always, very interesting.
Sorry, Mamta, just 2 minutes. So because, like I said, this is heavy for everybody to digest, we are giving you all time to do your exercises. So you can mail your exercises till the 20th of November. Okay. And so that will give you enough of time to revisit the videos as well as the material that we've done. And by 20th November, we'll see, we will check on which are the, who have sent the exercises, right? So that's the time you'll have to digest all this material that we did. Yeah. Mamta, sorry.
Yes. All right. Okay, so I'll just share the last slide, and we will wait for your questions. And if you have no more questions, then we will stop here. So just quick share. Yeah, yeah, right. So, right. So send your exercises to Priya for all the 5 days. Remember, the one who has done everything and completed all the exercise will be the one who will be given the best participant certificate. Please fill the feedback today for this particular training program, and let us know how you found this training program, if it was useful for you, and which day was particularly more useful for you, and if what all would you like to see in the next training programs. You can also suggest some topics, so that we can organize those particular topics as per your needs. Besides that, please fill the 3 minutes online survey form for Women in Astronomy. It was mostly for researchers, junior, senior level, but also students can participate, not very young ones, but masters and above. And besides that, we have this is the certificate of participation. So if you need this certificate of participation, then please let us know, and you will also fill it in the feedback form for this training program. And finally, I would really like to thank all the participants, because they have been very positive. They have been also they have been showing their interest until the end. So that's really great. And that is really nice. And I'm sure they have benefited out of this very nice training program that was organized by Priya and Professor Hassan Hassan. So once again, we acknowledge the support of Professor Hassan Hassan as well as Priya Hassan, and all their excitement and their generosity and their interest in giving such kind of training programs to students from all over the world, and their help with this training program. So Thank you very much. And if anyone has anything to say, then please unmute yourself and you can say whatever you feel like.
Yeah, it was a pleasure to participate, and I hope it was of use to the participants. And if they need help, they can be in touch, and we'll be there to troubleshoot. And so what we have done is just to insight them into the resources which are available, and the participants are requested to work through the exercises and work beyond what is being asked for them to do. Yep. Thank you.
Thank you, everyone. And we hope to see you all soon in another training program.
Thank you. Thank you, ma'am. Thank you, ma'am.
Thanks, everyone. And for the feedback form.
I have a question now.
Yeah, that's
one question about the form.
And, see you. It's time up, I think. Are there some questions?
Yes,
no, there, are there
yes, Modo, you can ask the question.
Okay, thank you for your presentation.
Somebody inquired about the email. I've written that again.
Okay. I don't see the link.
Somebody want to say something?
I don't see the link.
Are you saying
yes.
something?
Okay. Hello? Hello?
Yes, please, go ahead.
How you hear me?
Yes, we can hear you. Please go ahead.
Okay. Thank you for your presentation. So, about the form. I don't see the link about the form. I just see the first form update one, the first day.
Oh yes, okay. You see the form just on the first day. Yes, indeed.
Yes.
And
yes.
that is because you have filled the form already, so you can't fill it again. That's the reason. It was to be filled only once because I did not change it for other days. And I had sent a message to you people that it won't be changed and please fill in the end. And the one who have already filled, thank you very much, because anyway, we had good comments from you.
Okay.
So thank you.
Thank you.
Yeah.
Thank you very much. Okay.
Okay. Are there any other questions? All right. If there are no more questions, then please remember to let us know if you need the certificate of participation. And thank you again. And I think we will stop the recording over here. And if you have any questions and you want to ask any other information, then please post your questions either to Priya on the email or on the Slack channel, and we will answer it over there. So I'll stop the recording here, Priya.